Hello everyone, this is another video on electrodynamics. We will be trying to solve Griffith questions. Alright, we had solved the Griffith questions from I think capacitance in the previous chapter. Let's solve more questions from potential and capacitance. Okay, so that we can just wrap it up like electrostatics, like the basics. We can wrap it up and we can move to the next chapter. All right. So find the potential inside and outside a uh, uniformly uniformly charged solid sphere, okay, whose radius is r capital R and the total charge is q. Use infinity as your reference point. Compute the gradient at a gradient of v in each region. All right, and check that it yields the correct field. Sketch VR. Okay, so you are asked what potential inside outside a uniformly charged in a solid sphere, and you are asked potential inside and potential inside and outside the uniform charge solid sphere whose radius is r and total charge is small q. Okay, use infinity as your reference point. Compute the gradient of v in each region. Check that it yields the correct field. Okay, so we know potential is vr is equal to minus infinity to r e dot dl. Why infinity to r? Because the definition of electric potential is to take a charge from infinity to a distance r. That is your potential. Okay, so we have to find inside and outside. Okay, so for that we need to know the electric field inside and outside the solid sphere, isn't it? So electric field we have to know. Electric field outside the sphere, that is r greater than r, is how much? E is equal to 1 by 4 pi epsilon naught q by r square, isn't it? That's a simple one. Q by r square r cap. Inside the sphere, at a distance, inside the sphere, the radius of the sphere comes to the picture. Okay, inside the sphere, this is out. 1 by 4 pi epsilon naught q by r cube into distance r, whatever distance we have to calculate, r cap. Okay, inside the sphere. Yeah, so we now know this. Now we can just put these values here. In the formula potential, we will get the what a potential inside and outside a uniformly charged sphere. So let's first calculate outside point. So v out is equal to minus infinity to r. Okay, minus infinity to r. E is how much? 1 by 4 pi epsilon naught q by r square. Okay, yeah, q by r square r cap, q by r square r cap, into dr r cap. Okay, yeah, so that will give me 1 by 4 pi epsilon will go out minus 1 by 4 pi epsilon naught. Q also comes out, infinity to r, dr by r square. R cap dot r cap is 1. Okay, dr by r square is minus 1 by r. So if I write it here, minus q by 4 pi epsilon naught minus 1 by r, infinity to r. Okay, so minus q by 4 pi epsilon naught minus 1 by r minus 1 by infinity. That is how much? That is this 1 by infinity is 0, we know. So q by 4 pi epsilon naught r. Okay, this is your v out. Okay, this is a v out. Now we have to calculate inside point, inside the sphere, v inside. Okay, is equal to minus infinity to r e dot dr or dl, whatever. Okay, so here see, When I'm saying inside the point, that means somewhere here r distance. So how, what is the definition of potential? To take the charge from infinity to that distance. So infinity to this distance first, the surface distance is r from the center because it's radius. Then this distance to the distance. So we can divide the limit into two parts. That is infinity to capital R. That is the radius of the sphere. Okay. Minus infinity to plus minus minus. Sorry, plus minus r to r. Got it? Because r to r. Okay. E dot r. Is that all right? Okay. So if you see minus, what is the, this is what, this is outside point, isn't it? This is your outside point actually. So outside point, what is the electric field? 1 by 4 pi epsilon naught q by r square. Sorry, q by r square dr minus r to r. This is inside point. This is actually inside point, na? So inside point is 1 by 4 pi epsilon naught q by r cube r dr. Okay, is that all right? Yeah. So I'll just do it here. Okay. So minus q by 4 pi epsilon naught 1 by r square dr is minus 1 by r infinity to r minus q by 4 pi epsilon naught rq also comes out. R dr integration is r square by 2 r. Okay, so if I write it again, so minus 1 by 4 pi epsilon naught, so q by 4 pi epsilon naught minus 1 by r plus 1 by infinity minus q by rq r square by 2 minus r square by 2. Okay, so q by 4 pi epsilon naught r minus this is 0, q by 4 pi epsilon naught r cube r square by 2 plus q by 4 pi epsilon naught r cube r square by 2. So q by 4 pi epsilon naught r minus q r square by 8 pi epsilon naught r cube plus q by 8 pi epsilon naught r. Yeah, I can add these two. So that will be q by 4 pi epsilon naught r q by 8 pi epsilon naught r q r square by 8 pi epsilon naught r cube 3q by 8 pi epsilon naught r q r square by 8 pi epsilon naught r cube. Yeah, so that is the answer. Okay, if I take this q by 4 pi q by 8 pi epsilon naught r common, that will be 3 minus r square by r square. Yeah, so this is the total potential inside. Okay, I hope you understood this one. It's not hard, it's a bit just derivation is there. Hmm. But if you practice it, you can remember this value q by 8 pi epsilon naught r over into 3 minus r square by r square. Yeah, this question is done. Next, problem 2.2. Find the potential at a distance S from an infinitely long straight wire that carries a uniform line charge lambda to the gradient of your potential. Check that it is correct. Okay, see, potential at a distance is infinitely long straight wire is this one. Suppose it has uniform line charge lambda. Find the potential at distance s. At distance s from the this one from line charge lambda. Compute the gradient of your potential and check that it is the correct fit. Okay, so for this again we need to know we need to potential is asked. Okay, potential is asked. So mm, infinity to s it will be this time v dot ds. The distance is ds, no? So ds. Let's take ds. Okay. So this is not area. Okay, this is distance this s here. You may be thinking this is a flux for no. Okay. For this we need to know the electric field also for a line charge and line charge. Electric field for linear charge distribution. Linear charge distribution is equal to 1 by what? 4 pi epsilon naught r, 4 pi epsilon naught 2 lambda by r, if you know r. That means here r is s, so s. Okay, you have to adjust the denote like the notations and all. 2 lambda by s. So I will just put it there. So v is equal to okay. See here. Uh, Let me take a distance from a from I'm taking the charge from a distance a to s. Okay, so I will take the limit as a to s. All right, e dot ds. Yeah, a to s. Okay, so a to s. What is a e? 1 by 4 pi epsilon naught 2 lambda by s cap dot ds s cap. Yeah, now just what will I do? 2 lambda by 4 pi epsilon comes out, minus is there, a to s ds by s. Now minus 2 lambda by 4 pi epsilon naught. Uh, the integration of ds by s is ln, yeah, ln s. So ln s a to s minus lambda by 2 pi epsilon naught ln s minus ln a, which can be written as minus lambda by 2 epsilon naught ln s by a. Okay, so this is the electric field. If I give a sign, no, this is a potential. Sorry, yeah, potential. All right. See how easy it is. Hmm? Why I took A is here A, because C, if we take infinity, suppose I took infinity. See, it would have come. I'll show you. It would have come ds by s integration infinity to s. Okay. See, integration ds by s infinity to s. This I'm saying why I took A in place of infinity. See, ln s infinity to s. Now ln s minus ln infinity. What is ln infinity? Do you know what is ln infinity? We don't have any idea what is ln infinity. So I just left it. I just took a point A. Is that all right? Yeah. Okay. Compute the gradient of a potential. Check that it yields the correct field. Okay. Let's do it. We got this potential. So he is saying check it whether this is the correct potential. This is the electric field. So gradient will be how much here? As del by del s, isn't it? Because s is the variable here. Del by del s, um, s cap, isn't it? S cap del by del s, lambda by 2 pi epsilon naught ln s by a minus s cap lambda by 2 pi epsilon comes out del by del s of ln s by a. So minus s cap lambda by 2 pi epsilon naught. This one will be 1 by s by a into derivative of s by a, that is 1 by a. 1 by s. So this one will be minus 2 pi lambda s. Isn't it your electric field? Hmm. Yeah. Yeah. Very good. The minus here. Yeah. Okay. So this is there is a minus here. Oh, did I do a mistake? Might have done some mistake here. Okay, just check once and let me know in the comments if I have done some mistake. I think this is correct. Yeah, it's correct. Okay, this question is done then. 20. Number 2.2.23. For the charge configuration of problem 2.15. Alright. Find the potential at the center using infinite as a reference point. 2.15. Okay, in 2.15, okay, 2.15, what was happening? Electric outside was telling you from the book. Okay, k by epsilon naught, um, b minus a by r square. That was your electric field for outside point. Electric field for inside point was in 2.15. Electric field inside was k by epsilon naught. Don't worry, this should be able to do it when you're doing from the book. Okay, Griffith. Okay. This is third edition book. Okay. Yeah. So let's do it now. So potential at the center using infinity as your the potential at the center V0. There will be my infinity to what? Center 0 E dot dl. So to reach the center, what we have to do? We have to go through some points. Infinity to B, k by epsilon naught, b minus a by r square. Yeah, it's like this. Okay, this is A, this is B. Now from B to A, yeah, from B to A, from B to A, k by epsilon naught r minus a by r square. Sorry, I'm leaving the yeah, minus a to 0, because we have to reach the center, right? We just cannot leave it here. Um, Center, and this the electric field inside was 0. If you remember. Yeah. So now we just have to do the integrations. So the first one, what will happen? K by epsilon naught b minus a will come out, and it will be minus 1 by r2. Okay, I'm just writing roughly. So what will happen here? K by epsilon will come out. Okay. B minus a will come out. Minus 1 by r. It will be infinity to b. Okay. There is another minus actually in that side. So then minus k by epsilon naught. Okay. Okay. Let me write it again. B to a r minus a by r square dr. 0 0 minus 1 by b 1 by infinity k by epsilon naught b to a. Okay, see here what will happen is I'll separate it. 1 by r squared dr minus uh, a by r squared dr k by epsilon naught b minus a minus 1 by b k by epsilon naught. This is 1 by r dr is ln r, isn't it? Ln r b to a minus plus a by r b to a. This is a k by epsilon naught b minus a hmm, minus k by epsilon naught ln a by b plus a by a minus a by b. Is that clear? That will be k by epsilon naught b minus a minus k by epsilon naught ln a by b plus 1 minus a by b. Okay, that's right. Yeah, this is the answer. Alright. Hmm. Okay. Oh, we can expand it a bit, and I think we'll get something. No, no, leave it. Okay, okay, let's do it then. K by epsilon naught b into b minus k by epsilon naught b into a minus k by epsilon naught ln a by b plus k by epsilon naught b, so minus, and minus plus k by epsilon naught a by b. Okay, this one, these two will be cancelled out, isn't it? This is one. Yeah, sorry, this is also. Yeah, this one will also be cancelled out. This is plus. So answer will be k by epsilon. You do it yourself, this one, okay? I just did it a bit roughly because I know you can solve it easily. No need for me to solve it separately. Okay? Yeah. So next question you see, this one, 2.24. Again, another configuration. So these questions are really connecting themselves. See, a cylinder is given in the question, so you can think about that. You don't need under problem 2.16 for this. Potential difference between a point on the axis and a point on the outer cylinder. Note that it is not necessary to commit yourself to particular reference point. So the outer cylinder, that question is this one. Okay, anyway, leave it then. If you don't have, I don't have the reference. Okay. Find the potential of a uniformly charged spherical cell of radius r. This one, do it. This is very easy. This one you should be able to solve. It's very easy. Take your time and solve it. I'll do the diagram for you. So you can sell y-axis, x-axis, z-axis. This is where we have, for example, we take an element, okay, of this sphere. So element, this is r, theta dash. The point will calculate because of this element, and the distance is r, small r. Okay, this is a straight line, just it is curved because of the space-time curvature. So this is it. So calculate the distance that one at point P. Okay, so we know what potential is 1 by 4 pi epsilon naught. Yeah, hmm. Sigma dA by r. Sigma dA dash I'm giving here because it's like, let's take dash. So sigma dA as is like charge distribution. This is charge distribution, alright. So here from this diagram we can say r square is equal to what? R square plus z square plus minus 2 rz cos theta dash. You have to remember this expression, okay, for this kind of situations. R square plus z square minus 2 rz cos theta dash. Hmm. Yeah. So an element of surface area on the sphere is what? What is the element? Element of surface area. dA dash, element of surface area is how much? R square sine theta. We know it. This one, you know. Sine theta dash. So you know everything theta. Theta dash d phi dash. Yeah. Hmm? So 4 pi epsilon naught Vz along z axis, if we have to calculate, would be how much? I just took this one to this side, okay? So that for simplicity, sigma I can take out, okay? In place of dA dash, I will just put r square sine theta dash d theta dash d phi dash, okay? Whole divided by r square plus z square minus 2 rz cos theta dash, okay? Yeah, yeah, that's one. So now what? Now see, this is not a single integration. This is double integration for d theta dash d phi dash. So sigma, if I do, r will come out, r square will come out, right? R square comes out. Hmm. And see, this is for sine theta dash d theta dash. This one is r square plus z square minus 2 rz cos theta dash. Okay, this is 0 to pi. Then d phi dash is another integration. This is always 0 to pi. Yeah, this sorry, this is 0 to 2 pi. So we know this integration 0 to 2 pi, so 2 pi will come out. Now you just have to do this one, 0 to pi sine theta dash d theta dash divided by r square plus z square minus 2 rz cos theta dash. Okay, now what is the integration of this? We have done it before, so you just have to remember this one. Solving it will take so much time. You just have to remember the value, that is 1 by rz. Okay, the whole root over will go to the upper part. Numerator r square plus z square. Just have to remember this, 2 rz cos theta dash. Okay, and 0 to pi. 0 to pi. Yeah. So I'll just put the pi in place of what? Theta dash, not the z or r. Theta dash. Theta dash is the variable here. So if I put it here, 1 by rz. Let's take 1 by rz outside. R square plus z square minus 2 rz cos pi is minus 1, so minus is plus, minus r square plus z square Cos 0 is 1. So is that all right? Hmm? Is that all right? So I can write this one as what? If you see carefully, R will be cancelled. R by Z. This one is what? Inside the bracket R plus Z whole square. And this one is what? If you see R minus Z whole square. So 2 pi sigma R by Z. This is R plus Z minus R minus minus Z, that is R plus Z. So R cancelled. So this is 2Z. 2 pi sigma R by Z into 2Z. So ZZ will be cancelled. So 4 pi sigma R. Okay. Yeah. Okay. So this is your what? This is actually your in the left side. What was in the left side? 4 pi epsilon of Vz. 4 pi epsilon naught Vz. So if I do this, Vz is sigma r by 2 epsilon naught. Okay. Sigma r by 2 epsilon naught. But see, this is wrong. This is actually wrong. We should not have opened this one. See, here what will I do? I will do this. I will keep it that way only. Okay. Let's keep it this way. But the thing is why? Because we must be really careful to take the positive root or negative root. Okay. For points outside, so for outside points actually, z is greater than r. Okay. So root over of, let's see, let's keep it this way. So root over of r minus z whole square should be z minus r. Okay. Because z is greater than r. So I can put it here. Vz is equal to, okay, 4 pi epsilon Vz is equal to 2 pi r sigma by z plus z minus, this should be z minus r. Is that all right? So 2 pi sigma z, sigma r by z, this is r plus 2r. Okay, this becomes 4 pi r square sigma by z. If I take 4 pi epsilon, this side 4 Vz is equal to 4 pi r square sigma by 4 pi epsilon naught z. Okay, so r square sigma by this one. Okay, this is for what? This is for outside points. Now for inside points, what? Z is less than r, so I can just take it as root over r minus z square root over is equal to r minus z. Okay, so Vz should be 2 pi r sigma by z r plus z minus r minus z. Cancel 2z. So 2 pi r sigma by z 2z 2z by 4 pi epsilon naught. Z gone 2 2 2 2. Right. So r sigma by epsilon. Okay, this is your inside point. So Vz is equal to r sigma by epsilon. This is your inside point. Okay. Yeah. This is the question. Okay. But see, sigma is, we know sigma. Sigma is what? Q by 4 pi r square. So if you put Vz outside in place of sigma, we will just put this r square sigma by epsilon of z r square q by 4 pi r square epsilon of z. So 1 by 4 pi epsilon naught q by z. Okay, yeah, and for inside vz in v r sigma by epsilon naught, that is q by 4 pi r square epsilon naught. So 1 by 4 pi epsilon naught q by r inside. Okay, so this z you can take also r. Okay, no problem. Vr is equal to 1 by 4 pi epsilon naught. Any distance, no problem. Is that all right? Is it okay? This is the way to solve it. Hmm. Yeah. Next question. Try this question. In problem 2.45, please try. I will solve it eventually, but you try once. Okay. So here, first of all, we need to again know to calculate the potential. Sorry, energy. We need to know the electric field. Okay, we need to know the electric field inside and outside the sphere because why? Because energy formula or work done formula is what? It's formula epsilon by 2 integration of E square dV. dV is a volume element. Okay, so for that we need to really know. So we know. Let's calculate it. All right. Hmm. So epsilon naught E dot dA is equal to how much? Q enclosed, right? Q enclosed. Hmm. So if I put the value here, see, Q enclosed is rho dV, isn't that true? Yeah, rho dV, which is equal to rho. Rho is how much? Rho is given actually, Kr. Yeah, volume charge density is given Kr. R square dV is R square sine theta d theta d phi dr. Okay, yeah. So I can do this here. Kr q dr integration 0 to r sine theta d theta integration 0 to pi. and d phi is your 0 to 2 pi. Yeah, this will be kr fourth by 4 into 2 into 2 pi. So that is kr fourth by 4 into 4 pi, that is kr 4 pi. Yeah, kr 4 pi, isn't it? So this is a Q enclosed actually. This is a Q enclosed. So electric field is what? See, E dot dA, epsilon E dot D is equal to kr 4 pi. So for inside point, for r less than r, okay, for r less than 1, what it will be? It will be simple, this one. Electric field will be what? What will be the electric field? Okay, anyway, wait. So Q enclosed, I will say Q enclosed for r less than r will be k r 4 pi. For r greater than r, what it will be? For r greater than r, what it will be? Hmm. It is simply capital R, isn't it? Yeah. Okay. See now what? Okay. Now see. Um, Now we will use this to calculate your electric field. Okay. And if you calculate electric field actually, so your E inside will become k by 4 epsilon naught r square. Okay. And what will be E outside? E outside will be k r fourth by 4 epsilon r square. Okay. Okay. These things you have to do. Yeah. Do it yourself. So what done will be how much? Epsilon by 2 e square dv, isn't it? E square dv. So epsilon by 2, first of all is 0 to r. Okay. 0 to r k r square by 4 epsilon. This is the inside point. Hmm. What is dv? 4 pi r square dr. Dv is, we know, 4 pi r square dr. I just put it on. Plus epsilon by 2 r to r. This is your r to infinity. Outside point, r to infinity, outside point is this one, k r fourth by 4 epsilon naught r square, 4 pi r square dr. Yeah, yeah. Okay. So this is 4 4 cancelled out. Everything will go out 4. This is 4 4 cancelled out. Okay, r square cancelled out. So everything goes out for this one. Yeah. Okay. Okay, my bad, my bad. This is e square, no, e square. I just put the values of e. Okay, okay, my bad. Okay, let's do it again. Yeah. Epsilon by 2, epsilon naught by 2, e square dv. So epsilon by 2, e square for inside point, e square will be kr square by 4 epsilon naught square into 4 pi r square dr plus epsilon naught by 2 r to infinity k r fourth by uh, k r fourth by 4 epsilon naught. Don't put pi here, okay? Square pi r square dr. Now if I open it, epsilon by 2, 0 to r, k square r fourth by 16 epsilon naught square 4 pi r square dr plus r to infinity k square r eighth by 16 epsilon naught square r fourth 4 pi r square dr. So if you do it, epsilon by 2, so k square 4 pi by 16 epsilon naught square r4 is r6 the dr 0 to r plus k square 4 pi r8 by 16 epsilon naught square by 1 by r square to epsilon by 2 uh, k square pi 4 epsilon naught square r6 by 6 r7 by 6 r7 by 7 plus this one. Try to do this from yourself, don't copy, okay? Because I am doing it myself. If you copy, there is no point. This should be done by yourself altogether. So if you put all the values and all, okay, at the end you will get pi k square r7 by 0 7. That should be the answer. Okay, that should be the answer. Okay, next question. Try this one. Okay, the relative potential of some configuration is given by the expression VR is equal to this much. A equal minus lambda r by r. Yeah. Where A and lambda are constants. Find the related field ER. Okay. Charge density rho r, total charge Q. Find the related field ER, charge density rho r, and total charge Q is how much? How will I calculate? Related field we know is minus del V. Let's just do it here. Minus A del by del R of minus lambda by r cap. Minus A minus 1 by r square e to the minus lambda r minus lambda by r e to the minus lambda r cap. So minus A r minus lambda r cap should be your A e to the minus lambda r 1 by r square plus lambda by r. This should be your electric field. Yeah. Alright. Now charge density is asked. Charge density is formula of what? What is the formula for charge density? Rho is equal to rho by epsilon naught is equal to del dot E. Yeah. So whatever I got in del is like E, I'll just put it here. So not del dot E. So epsilon naught del dot. Del dot E. So epsilon naught del dot A e to the minus lambda r 1 plus lambda r cap by r square. This was the expression, the total expression. So if I do A epsilon naught, and this is kind of a tough one, okay? This is Not that easy to do this one. Maybe this one first. Let's do it. Plus um, see. This is arcade. Arcade is arcade. So we know that del dot r cap by r square, that is written as 4 pi this. Okay, so let's write it down. Okay, just have to write it down. This. And, and we'll solve also this one. Yeah. This one that. Yeah. This one is number. This is number. Where we open it. This made one number or numerical minus number. Okay, this two will cancel out. This is it. Minus lambda square equal to minus lambda r into after. Yeah, and this one is this one. So just we have to put everything here. Yeah. So row will be what? Row will be if I say row will be your epsilon a, if you put everything 4 pi del q r minus lambda square by r. Alright. Now charge is asked also. Yeah. Charge is asked. Total charge. Total charge will be Q is equal to rho dV. Okay, so this one again, put everything here, epsilon A, 2 pi del Q R minus lambda square by R equal minus lambda R dV. Hmm. So dV is actually what? 4 pi R square dr. Yeah, so just have to put it here. Epsilon A, 4 pi Q R into another 4 pi is there actually. R square dr minus lambda square by R. Epsilon A. It is what minus lambda R. Square 4 pi dm. This is the one. So if you calculate all this, you will get this is your R, this is R. Everything will come out, and this is actually 4 pi. Okay. So, there, and this one will be 0. Right? This is 0 to infinity. The whole thing will be 0 because R e to the minus lambda R in 0 is 0. Okay. So if you calculate, you will get Q is equal to 0. If you just put the values. Right? Yeah. Okay. So this through this question, everything like we could cover. Let's try this one. 2.47. No, this one 2.51. Try this question is a longer question. Like you have to read patiently. So I'm giving you to read. I'm giving you time to read. All of electrostatics follows from the 1 by r square character of Coulomb. So that is inverse square law. Together with the principle of superposition. Okay. Together with this one. An analogous theory can therefore be constructed for Newton's law of gravitation. What is the gravitational energy of a sphere of mass and radius r, assuming the density is uniform? Use the result to use the result to estimate the gravitational energy of the sun. The sun radiates at a rate of this one. If all this came from stored gravitational energy, how long would sun last? Yeah, this is the question. Read the question two, three times. Okay, read the question two, three times, then only try to solve. Otherwise, I will solve it eventually. Okay. So, see what is gravitation? G m1 m2 by r square. Okay. This is gravitational force. What is Coulomb force? 1 by 4 pi epsilon naught q1 q2 by r square r cap. Yeah. Okay. So, gravitational energy of a sphere is how much? Okay, remember this. Gravitational energy of a sphere. Gravitational energy of a sphere is double gravitational is equal to 3 by 5 g m square by r. 3 by 5 g m square by r. Alright. So we know the values of everything like 6.67 into 10 to the minus 11 Newton meter square per kg square. Then your mass of the sun is 1.99 into 10 to the power 30 kg. Hmm. Radius of the sun is 6.96 into 10 to the power 8 meter. Okay. Sun's gravitational energy, if we put all the values, 3 by 5 is equal to into 6.67 10 to the power minus 11 mass of sun. 9 and 10 to the power 30 divided by r 6.96 10 to the power 8. So if we put all these values, the answer will be 2.28 10 to the power 41 joules. That is the gravitational energy of the sun. Okay. So in at this current rate, energy will be dissipated in a time t. Okay. So that is your how long will the sun last? Isn't it? That is the question. So time will be what? Work by power, isn't it? Because work is equal to power is equal to work by time. So if I interchange T is equal to W by P. So W is a 3.28 10 to the power 14, 41. We calculated this. Huh? And power of the sun. Okay. Power of the sun is what? This radius at a rate of this what? This is the power of the sun. 3.8 10 to the power 26. So if you do this, this will be giving you 1.87 into 10 to the power 7 years. That is your time. Sun would last this much. Is that all right? Yeah. Okay. So these were the questions from Griffith that we did today. I hope you understood this lecture. Okay. And I hope to bring more questions from Griffith that will really help you in entrance exams. Okay, so these are a bit longer type questions. Okay, but you need practice. If you can practice this, you can solve it faster. And it's not like it's only for entrance exams. See, if you go somewhere to teach, you just cannot skip the derivations and just go direct. Like this is a formula, this is a formula, this is a numerical. No, you have to do the derivations because derivations will are giving us the idea that how to solve, how to get that electric field, how to get the electric potential. That is important, not the formula. Formula will give me only the values and the answers of the questions, but how it is derived, we should know. We should know, right? Yeah, as a physics student, as a physics teachers, we should know how to derive this. So that we can teach somewhere, we can teach others also. Okay, it's not like just skip it. Okay, yeah. Okay, then thank you very much. See you in the next session. Thank you.